right? And let's look at this matrix. Minus 3 half, 3 minus half, 1 0 0 0 1 0. Okay, let's say a to the 100. Yeah, pretty large. And the eigenvalue of the matrix. Okay, we can see that we get one eigenvalue that's pretty small, one that is exactly equal to 1, and this one calls for trouble. Right, minus 2.6861. And I don't know if I still have the figure, but if you plot the solution, okay, let me just plot it with do you see what's the ratio? What's the ratio of the magnitude of one point to the last point? This is still pretty small, so let me actually just plot it when you have a large enough. Well, it's actually maybe 500, maybe 700. Yeah, now you get to a magnitude of normal values. So if I can zoom in into the last portion of the picture, right? Look at one value. How can I? Right, 3082 versus the next value minus 2072, right? That's roughly the magnitude of the eigenvalue that causes the trouble, right? Minus 2.68. So what we see is that the solution actually very faithfully blows up according to the eigenvalue of the matrix.
The largest eigenvalue?
The eigenvalue with the largest magnitude. So why is that the case? Why is that the case? When you look at our previous analysis, right? I mean, here we have a 3 by 3 matrix instead of a 2 by 2 matrix. And you can see like how the matrix grows. You can see what determines the magnitude of the matrix is actually not the eigenvalue that's small. It's the eigenvalue that is big that determines the magnitude of the matrix. When you multiply this diagonal matrix, right, some contains a huge number, right, like 10 to the 40 or 100. Some contains pretty small numbers on the order of 1. And then you mix these numbers by multiplying, left multiplying something, right multiplying something. What ends up to the magnitude of the matrix? What matters? The eigenvalues that are small doesn't matter anymore, right? I mean, it gets mixed. These tiny numbers get mixed with these huge numbers. Only the huge numbers matter at the end. So whichever eigenvalue that has the biggest magnitude, that's the one that matters. Okay. By the way, I'm gonna give you an answer. I mean, does anybody have an answer to my previous question? If the matrix is like that, has a +1 as opposed to -1, how would it grow? What is the eigenvalue that matters? Well, I mean, it's a little bit unfair. You don't have MATLAB. So I'm going to calculate the eigenvalues for you. It's going to be 1 plus minus I. Okay? So if I take this matrix to the 100th power, what's the magnitude of that matrix? Somebody guess? Oh, 100 is a little bit difficult to do. Yeah, I mean, 100 is fine. What's the magnitude? Huh?
Maybe like the magnitude of the largest eigenvector to 100.
Right, the largest eigenvalue to the 100. And here the magnitude is what? Square root of 2, right? Square root of 2 to the 100 is like 2 to the 50, right? 2 to the 50 is something like, I know 2 to the 10 is like 1,000, right? So 2 to the 50 should be something like 10 to the 15, right? 10 to the 15. So, yeah, basically, whenever you analyze the stability of something, so this lecture is just a very first introduction of the effect of stability in numerical method. But such analysis is going to be pretty much everywhere, right? So here we are looking at numerical methods. We are deriving a scheme for something, right? In the future, maybe not in relation to this course, but like you may have to derive a model. I mean, not even numericals, model for describing some engineering phenomenon or natural phenomenon. Stability matters, right? And it's not just the matters a little bit, just it determines if something completely works. I mean, something works or doesn't work at all, right? I mean, the way schemes blow up is not something you can rescue by tuning stuff. It's just doesn't work at all. So being able to know the stability of something you devise is going to be very, very important. So next lecture, we are going to be studying how, basically, when you derive a stable scheme, the stability still matters. Okay, so we are going to analyze different levels of stability, right? So in this case, we are looking at a scheme that is completely unstable. I mean, there is no rescue. But for schemes that are stable, there are different levels of stability. There are things that are more stable, there are things that are less stable. And we're going to be analyzing, we're going to be looking at how the level, different level, quantitative level of stability is going to affect the quality of our solution. All right, I will see you next Tuesday, I think. Right, Tuesday is going to be Monday schedule. All right, see you.